Hey, hello everyone. This is lesson 4 in module 1 for the contemporary math class. I will be reviewing the nature of the solutions of a system of linear equations. Again, you should have this note sheet up in front of you for those students that are working through this, and so you can follow along. We're actually going to skip down from that first page there to the lesson summary like we've been doing. Okay, and so to kind of give us a clue about what we're doing here. So a system of linear equations can have a unique solution, that's 1. No solutions, that'll be 0 solutions. Or infinitely many solutions, so we can use like the symbol infinite there to help us there. Okay, in the previous lessons, we saw the unique solution situation where the linear equations, the line equations, intersected in a single point. But no solutions would indicate that we don't always have to intersect, right? They might not intersect at all. Or infinitely many would be the situation where the two lines are the exact same. Systems with a unique solution will be made up of linear equations that have different slopes that graph as distinct lines intersecting at only one point, right? So it looks something like this. If there's my axes, then you might have like, two lines that intersect like this. And there's our solution point. Systems with no solution, so there's 0 solutions, right, will be made up of linear equations that have the same slope that graph as parallel lines. In other words, they won't intersect, right? Parallel lines never intersect, so that might look like something like this. Right? These two lines look like they'll never intersect, so there's no points of intersection. Finally, systems with infinitely many solutions will be made up of linear equations that have the same slope and y-intercept that graph then as the same line. And so they'll look something like this. Well, it's hard for me to completely overlap it, but you get the idea, okay? They completely overlap one another. And so it looks like it's one line when there's really two lines on top of each other. That indicates there's infinite solutions because these two lines intersect everywhere along each other, right? There's a point of intersection here and 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 here, 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 here. You get it. There's an infinite number of points of intersection all along that line. Okay? So, other methods we can use to solve systems. We can also solve systems using a substitution method. Okay? And you'll see an example here where these equations are both equal to y. Right? And so since they're both equal to y, we can set them equal to each other and then solve for x. And then once you solve for x, you can plug it back in to solve for one of those equations there to solve for y. Alternatively, right, we sometimes have to do some other manipulation. So for example, right here, okay, we can see that x is equal to y plus 5. So that means this x right here we can replace with this y plus 5, substituting it in. Okay? So it looks something like this. This equation would become 3y plus 5 equals 4y plus 2. And then you distribute the 3. And then solve the equation for y. And get your y coordinate and then plug back in to get the x coordinate. Okay, so let's see an example of this. Scroll back up here to the first question. All right, so in here, we are asked to determine the nature of the solution to each system of linear equations. And we're going to use substitution. You could graph these if you wanted to. You would need to solve this one for y, but right away I can see that you're going to end up with some fractions. So let's try with substitution here. Okay, so with substitution, we can already see here that we have y is the same as negative 3/4 x plus 1. That means this y I can replace with this 3/4 x plus 1. So let's go ahead and do that. So I'll have 3x plus 4, parentheses, negative 3/4 x plus 1. Equals, plus 1 goes in the parentheses there because it's part of the y. Okay, so there's my substitution. Again, this is replacing the y. And that's equal to 5. Again, that's just coming from that little 5 right there. Okay, we'll distribute the 4. 4 times negative 3/4 is negative 3x. 4 times 1 is 4. These cancel out. 3 and negative 3 make 0. And so we get 4 equals 5. Now that's a strange situation. When does 4 equal 5? Pause the video and think about that. 4 never equals 5. And so, since we arrive at this impossibility, there is no solution. Okay? If you graph these two equations, you would see that they never intersect. They're going to be parallel. So no solution here. All right, I'll pause the video. I'll stop the video here, and we'll do some more examples in the next video.